Precalculus, Chapter 2, Section 2, Quadratics. And this is Part 2 of the notes. So let's start at Example 6. Graphing a quadratic equation in standard form, ax squared plus bx plus c. And so the first step is determine how the parabola opens. So we look at the a value. Since this one is negative, our parabola is going to open down. Now, rather than completing the square and put it in vertex form, we're going to work with standard form. So we're going to find the x value of the vertex, and we can use the formula, the opposite of b, divided by 2a. So I can take b, or the opposite of it, negative 4, divided by 2 times negative 1. So negative 4 divided by negative 2 is 2. Now to find the y value of the vertex, I'm going to plug it into my equation. And so I will get the 5 for my y value. So my vertex is the point 2, 5. So that's another way to find the vertex of a quadratic rather than converting standard to vertex form by completing the square. So using that little formula of negative b divided by 2a to find the x value, and then plug that in to your equation to find the y value. Now we'll find the x and the y intercepts the way we were doing on earlier examples. So x-intercept, we plug in 0 for y. And actually, what I'm doing is, since I'm in standard form, I'm just going to solve it using the quadratic formula. Sometimes we'll need to estimate. We won't have a parabola that's crossing on integer values. And so our two values where this one is crossed is negative 0.2 and 4.2. So remember, you have lots of options to solve a quadratic. You can solve by square roots if possible, you can factor, and then you can always use the quadratic formula. Now the next step is we're going to find the y-intercept by plugging in 0 for x. And in standard form equation, our y-intercept is always our c value. So we have the y-intercept 0, 1. So now we have our points that we can graph. So we're going to graph our x-intercepts, our y-intercept, and our vertex, and then get that fifth point by symmetry. And then let's just go ahead and draw our axis of symmetry where x equals 2. Let's talk about minimum and maximum points in a quadratic function. So let's consider the standard form, ax squared plus bx plus c. If a is greater than 0, that means our graph is opening upward, and so that means that that graph or that equation has a point that is at the lowest point. It has a minimum value, and it occurs at the vertex. So where x equals the opposite of b over 2a, and then the y value is the resulting value when you plug that into the equation for x. And the y value is the number that we say is our actual minimum value. Number 2, if a is less than 0, that means our graph is opening downward, so that our quadratic equation has a maximum value, and it occurs at the vertex, and we say the maximum value is the y value of the vertex. So in either case, the value of the vertex will help us find our minimum or maximum value, and we focus on the y value of the vertex to name that minimum or maximum. So let's look at this quadratic equation and just get some information about it from its equation. So we have it, we notice that it's in standard form. We're going to, without graphing, determine whether the function has a minimum value or a maximum. So our a value is positive 4. That means that our graph opens up. So it has a minimum value. So now we can use the negative b over 2a to find the x value of the vertex. We plug in 2 to find the y value. And this y value will actually be our minimum value. So when we do the math of plugging in 2 for x, 984 is our minimum value. Let's identify this equation's domain and range. So the domain of a quadratic is all real numbers. Our range since it opens upward, are all the numbers that are greater than or equal to the y value of the vertex, 984. Here's how we write domain and range in interval notation. So all real numbers goes from negative infinity to positive infinity, so we write that in interval notation. And then our range goes from 984, that's the lowest value, so it goes on the left, comma, and then positive infinity. So all the values that are infinitely greater than 984. Sometimes you'll have problems that you'll need to solve that involve maximizing or minimizing a quadratic situation. The first thing you want to do is read the problem carefully and decide which quantity it needs to be maximized or minimized. You're going to use the conditions of the problem to express the quantity as a function in one variable. You're going to rewrite the function in the standard form, and then we're going to calculate that vertex that will give us our minimum or maximum value. And then we're going to look back into the problem one last time to make sure we have answered the original question that was posed. So here's an example where we are maximizing area. So you have 120 feet of fencing to enclose a rectangular region. Find the dimensions of the rectangle that maximize the enclosed area. What is the maximized area? So the first thing is decide what must be maximized or minimized. In the very last question, we can see it there. It is the area of the rectangular region. Step 2, we're going to express this quantity as a function in one variable. So we're looking back and seeing what we were told. We have 120 feet of fence to enclose the area. We know that area equals length times width, so we're going to call that x and y. And 120 feet of fencing, we can think of that as a perimeter length. So if x and y are length and width, we know that perimeter is 2 times length plus 2 times width, or in this case, x and y equals that value. Now let's go ahead and solve for y. So subtract your 2x over and then divide by 2. So now we have done it. We have this quantity as a function in one variable. So y, or f of x, equals 60 minus x. And then to finish, we're going to plug those values, x and 60 minus x, into our area equation. So now area equals negative x squared plus 60x. So in function standard form, a of x equals negative x squared plus 60x. So now we can calculate our vertex, or in this case, it will be, we can tell it's a maximum value because we know we needed to maximize and our a value is negative. So negative 60, that's our b value, divided by 2 times negative 1, and that'll give us positive 30. And this will be involved in our maximum. So we know that area is maximized when one of the dimensions is 30 feet. Now, step 5 is making sure we answered the original question in the problem. Well, we need to find out that actual maximum area. So we know, according to the function we came up with in this problem, is that area equals negative x squared plus 60x. And so we're going to plug in 30, that dimension that will maximize our area. When we do the math, we find out that 900 is our maximized area, 900 square feet. All right, that concludes our notes in Chapter 2, Section 2 of Quadratics.